Okay, so it's 6:05. We'll start because last time we waited and it was difficult to finish in time. So last time we were discussing fluid statics, and some of the concepts are still yet to be discussed. So I'll just quickly spend some time on them, and maybe then we'll move on to the fluid dynamics part of the course, which is relevant for the third week lectures. So till last time we like you know uh, this thing we saw how to calculate static pressure over a curved surfaces, and many a times that type of questions are asked in the gate exam, particularly for 2 mark question like that. So uh, hopefully you remember what we discussed last time, and if you go back, you'll realize that when there is a curved surface, what we do, we generally divide the hydrostatic force acting on it into two parts. One is vertical component and another one is horizontal component. Horizontal component is a pretty straightforward formula. Uh, you assume it as a, I mean, you look at the gate or whatever curved geometry is there, and you take its vertical projection in vertical plane, and then you calculate hydrostatic force pretty much similarly as that of flat vertical plate submerged in the liquid. And the center of pressure is the point from which the horizontal force acts on the curved surface. And for the vertical surface, for the vertical force component, we take the weight of the liquid or whatever liquid is above the curved surface, and that weight is the vertical force component, and it vertical force acts through the center of gravity of that imaginary or real water, or the imaginary or real fluid domain, which is on the top of the curved surface, like that. So uh, maybe you know uh, give me one second. I'll just take one simple example, uh, because I felt last time we did not do much examples. So this is gate question again. I think it's interesting. So okay, so okay, title will be maybe. mm, so this is 2001 gate question, previous year, mechanical engineering department stream. So mm, so we have a uh, semicircular type of gate, uh, like, I mean, it has some uh, spokes like this, and it has these dimensions are given in the question. And from the liquid level, this is the liquid, and the distance from the top to the center is h. And this is actually pretty standard template. I'm taking this question because many a times you will realize that this type of questions are, maybe the geometry will change, but it will be more or less similar theme only. For example, like, for just to get the familiarization, we are going to solve this question. So as I said, for curved surfaces, we divide the hydrostatic force into two components. So, okay, I'll write the full question first before solving it. So the question is, what are horizontal and vertical? So this was Fy, and in this direction it is Fx. What are Fx and Fy acting on this gate? One second.
Sir, here the hinge will be here, sir.
Pardon?
The hinge of the gate will be where, sir?
It is at the center, but just listen to the question whether this
Sir.
hinge part is required or not, that we will decide later. So acting on this gate with width W. So gate width is given, which is into plane of figure, and you have some options. I'll give those also, or maybe I'll not give the options, because if I give options, maybe it becomes somewhat easy. Anyway, so this thing, first we'll let's say we'll find the horizontal force. So what we do, let's say for Fx, typically calculation of Fx is easier. Uh, so let's say this is the gate again. So it has some ribs like this. So what we do, we take its horizontal projection. So if you do that, it will look like this. It will look like a rectangle if you take its horizontal projection and you are looking from this side. So then you'll see gate like this, and in question it is given that this width is W, and this we know it is a diameter, so it will be 2r, the total distance. And here this f of x will be acting in this fashion at Cp, center of pressure of that projected area. And f of x, as we have discussed, it is typically rho g into the area, which is W into 2r into the this thing CG of this projected area. So that will be at h by 2. Oh, sorry, here h is actually 2r. So that will be 2r divided by 2. So if you just simplify it, one second. I think here this 2r it will be yeah. So this 2r by 2 is okay. I think I should write it properly. So the horizontal gate is at the depth of h, right? So the hydrostatic force. Just give me one second. My laptop just restarted out of the blue. Anyway, I hope I am clearly audible, even though because of this thing. Am I
Yes, sir.
audible?
Yes, sir, you're audible.
Okay. So yeah, so this horizontal force will be rho g h. H is the distance from the top surface of the liquid into the area, into the this thing area of projected area. So that will be rho GH into W into 2R. So the answer is rho GH WR. So this is your Fx, and it will act through and it will act through center of pressure, which is at so now the thing is it will be H minus R plus 2R by 3. Correct now? 1 second. Actually, this was not asked in the question, but just for our clarity, I'm just confirming this. 1 second. Because typically in previous problems, the H was given from the top of the plate. Here it is given at the center of the gate. So let me just check once whether yeah. So this thing, 1 second. AP X bar. Yeah, so which is at so we have to take it from the top. So uh, see till the center it is H, right? But you know for this projected area, CP will be below the 2R point actually. So I should have drawn this line slightly below. So if this is the center line, Fx will be acting somewhere here. So here will be your CP somewhere, maybe at the center of the W, at W by 2 or somewhere. Yeah, so I should be careful about that also. So it will be somewhere center like this, because this is constant width type of gate.
So W is imaginary here, sir. W is, we don't know the length of W is not. It is, we have just taken W.
No,
anyway.
it was given in the question. If it is not given, many
yes,
times.
I got it, sir. I got it. Yeah, sorry.
So if it is not given, typically we assume it as a unit width, and whatever force you will get, it will be Newton per meter. The unit for that will be like that. So yeah, and the center of pressure will be it will be at H minus R, because that is your top point of the gate from the free surface, and plus for this 2R it will be at 2R by 3. So it will be plus 2R by 3, because this height is 2R, right? And we know that for a plate it is at total height. 1 second. No. It is 2H by 3, right, for a vertical plate. Yeah. So 1 second. Yes, for vertical plate it is 2H by 3. So it will be here it will be 2 by 3 into total height is 2R. So if you solve this, it is H minus R plus 4R by 3. So it is basically H plus R by 3. So CP will be somewhere here. Hmm. 1 second. H minus R plus 2 by 3 into 2R, 4 by 3, H plus R bar 3. Yeah, correct. So CP should be at the bottom half of the gate. That was the point, and this is correct. And now the second part, which was what is Fy. So for Fy, as I told you, we take imaginary, or maybe in this case it is a real, on the top of the gate there is a real liquid. So I can show it maybe in this figure only. So what we do, we take, let's say this is the end point of the gate, and this much weight of the liquid will be the force, vertical force acting at the gate, and it will be acting at the some point which will be the CG of this red shaded area. So this now becomes a uh, geographical geometry problem. So you have so maybe I'll redraw. So you have this much, 1/4 of the geometry here, and this much area you need to find out, and then you can multiply with the width and you'll get the uh, volume. So this is your gate, it is hinged like this. So again, this will be your let's say this is your area 1 and this is your area 2. So this is height h, and this is your r. So this is a semicircular gate, so this will also be r. So a1 is equal to h1 into h into r, because this is also r, so rectangle. And a2 will be so that this total area will be r square, this bottom square, and you need to minus the circular part out of this. So that will be r square minus total area of the circle is pi r square, but here it is only quarter of it, so it will be pi r square by 4. This will be your area, this A2 area, and then uh, you know total weight of fluid column. This is basically Fy. Fy is total weight of fluid column above the gate. So total will be total weight is nothing but mass into mg, then m is density into volume into g, and what is volume? Volume is total area a1 plus a2 into the width, correct? So this becomes rho g w. A1 is hr and a2 is r square minus pi r square by 4. One second, let me just check the answer. Yeah, so this is the uh, force acting on the gate, on the top of the gate. So actually we are solving it in a tedious manner, because there is a bottom half of the gate also, right? Which is something which we missed. So basically the gate is like this, no? Total half circular gate. This is also R. So there is one trick also to this, but before going that, I'll explain you the proper way. So you did the calculation for this part, right? So let's say this is Fy force 1, and since there is water below this also, so this everything is under water. So there will be buoyancy force on the bottom half as well, and there is a buoyancy force on the, or maybe the weight is acting on this side, and this will be Fy1, which we just calculated, and there will be some Fy2 also. So Fy2 will be basically the total area from this point. So that will be uh, A1 plus A2 and plus this area, uh, of the gate. So Fy2 will be, again, rho GW will be common, because that is same thing only. Only the area is changing, which is A1 plus A2 plus A3. Okay, and finally we want Fy, right? So these forces are acting in opposite direction. So Fy will be Fy2 minus Fy1, because see, the buoyancy is a net upward force, net vertical upward force. So therefore Fy2 will be more. And from maths also you can see, because we are adding A3, this Fy2 will be more. So if you do that calculation, what happens? Rho GW and A1 plus A2 plus A3 minus A1 minus A2. So basically, this only A3 remains, and A3 is the this volume of the semicircular gate, or maybe area of the gate in this case, because we are already multiplying it with W. So this becomes rho G W into pi r square by 2. So now, so if you are preparing for any exam or anything, and such question comes, what you should realize is, you don't have this much time to solve the question, right, in the exam. So you need to do this thing. 1 second. So just look at the question and you just realize that there are two forces, okay, and Fy1 and Fy2, but they are acting in opposite direction, and their CG is also on the same line only, so therefore we can directly subtract them. Otherwise, we can't do that also. But anyway, we are doing force balance, so we can do that. And you just remember that if some question like this comes, you just take this area, because in the end only A3 remained, right, in our calculation. So A3 directly you take from there, and just you do the simple weight calculation of that fluid. So yeah, so this was the question that we solved. Actually, there are multiple questions on curved surfaces that are frequently asked in GATE and other things. But since we don't have time to go into detail, we'll stop here with the curved things. Maybe you can solve some questions, and if you find any difficulty, you can ask me. That way we can maybe discuss later also. So now actually one more question that I found out later regarding the buoyancy. We'll take this, and okay, we're already at 6:30. Okay, we'll go to the next part. This equilibrium in this thing. This is curved surfaces that we dealt with. Then there are you know there are different cases which I had started earlier discussing in the last class, but we could not finish. So what we'll do, 1 second. Equilibrium conditions are there, right? Yeah, so equilibrium conditions are there, and it has two categories. One is for completely submerged bodies. Here only this Archimedes principle, that thing comes into picture. 1 second. Maybe the spelling is not right. 1 second, I'll just confirm what is the spelling of Archimedes. We say it so many times, but we don't remember the spelling.
Sir, it is ARCHI, sir. RKMIDIS.
Okay. Yeah, ARCHI.
MIDIS, sir.
Google says it is MEDES. So we'll go with the.
Yes, sir.
So it is Archimedes principle. can somebody tell me what it is, Archimedes principle? In simple terms also, if you can tell, it will be better.
So the volume that occupies the floating body, that is equivalent to the volume of the liquid that it displaces. The weight,
Okay, maybe I should not write
yeah,
it here.
weight of the body.
Yeah. So before going that, so if there are completely submerged bodies, then there is another case where the bodies are floating. So they are called as partially submerged bodies. So these two categories are there in this equilibrium conditions topic. So first we'll take the uh, you know fully submerged case. So this Archimedes principle is, what it says is that if any body is in equilibrium in the fluid, then the weight of the body is balanced by the net vertical hydrostatic force, which is, we call it as a buoyancy, and it is equal to the weight of the fluid that is displaced by the body. So this is what Archimedes principle is. So then, yeah, so actually Archimedes principle, you can write it here only. So what it says, the buoyancy force, one second, buoyancy force, which is net vertical upward force acting on a fully submerged body, will be equal to the weight of the fluid. One second. Yeah, I think it is weight of the fluid displaced only. Yeah, weight of the fluid displaced. Actually, Archimedes principle is valid for both the cases. Okay, for completely submerged and partially submerged, on like for all the cases, it is same thing only. But in case of completely submerged bodies, what you do when you say the body is in equilibrium, so so I like to remember it this way. So there are three cases. Uh, so this is first is called as stable equilibrium. Then there is something called as neutral equilibrium, and then there is something called as unstable equilibrium. So what I like to do when I used to study this thing for earlier exams, I used to take the example of balloon. Uh, this this hot air balloon is there, right? So it will have some person sitting in this part, and it will be uh, going up, going down, like that, depending on the density of the this thing, density of the fluid that is in the balloon. So most of the mass is at the bottom part, because gas is very light, and other things like humans and this carriage weight, all things are at the bottom. So the center of gravity, which we represent by G here, will be towards bottom. And then since the whole balloon is submerged in atmospheric air, so when it lifts off, it will also experience buoyancy force, because air is also fluid, and we are studying buoyancy here for completely submerged bodies. So in that case, what happens? There is something called as uh, center of buoyancy, which is represented by this point B. So it is a point at which buoyancy force acts. So at point B, there will be buoyancy force, and at point G there will be gravity force, which will be equal to mg. So let's say gravity force, which will be equal to mg. And as we know, when the balloon lifts off, it is assuming there is no horizontal strong winds. It's a normal day. In that case, there is no horizontal forces. So this is what stable equilibrium looks like. So and okay, this B point. One second. Center of buoyancy, which is denoted by B point. It is, as I said, it is the point at which buoyancy force acts, and it is actually equal to the center of gravity of fluid displaced. So because of this balloon and all other things, whatever air is displaced from the atmosphere, that volume's center of gravity, if you take, that will be the B point. So B and G both are center of gravities, but G is center of gravity as with respect to mass, and B is center of the center of gravity with respect to the volume of the fluid. So if this case is there, then it is a stable equilibrium when your B is above G. So this is the stable equilibrium condition. So I'll write it here. B above G. So your center of buoyancy, if it is above your center of gravity of the body, then it will be in stable equilibrium when it is completely submerged. And when they both coincide with each other, it will be a neutral equilibrium. And when B is below G, then it is an case where the body will overturn. So there is something called as applied couple, overturning couple. Maybe you can look into it, but since we don't have that much time today, also we'll not go too deep. But yeah, so this is the equilibrium conditions for completely submerged bodies. And when you come to partially submerged bodies, there is one more concept that comes into picture, which is metacenter, which will denote by M. So metacenter is the point of interaction of buoyant force and centroidal axis when there is a slight this thing deviation. For example, how should I show it? Because okay. Okay, let's say we have some body which is partially floating in a liquid, something like this. So this is your liquid surface, and let's say this is center axis, symmetrical body if you are taking, and buoyancy will be acting at the CG of the submerged volume, which will be this volume. I'm just highlighting it with the red length. So buoyancy will be at the center of that. So this will be your B point. And then for the whole body, if you get the center point, that will be your center of gravity, G point, which we defined in the other case also. But here what happens, since the body is not completely submerged, you have to check whether it is in stable or not stable equilibrium. So what you do, you just give it a push. So instead of like, you'll give it push from this side, let's say. So what happens, this vertical axis, which was the earlier case, now it will become something like this, right? Because you're applying some external force at the top, and the body is displaced like this. Maybe I should draw properly. So let's say like this. So what happens? Let's say this was your earlier B point and G point. Now, the new B point and G point will be because buoyancy force will change, right? Because when you displace the body, the volume displaced of the fluid will change. So your B force will be something at B dash, and there you will have buoyancy force at B dash, and your G point, it will be also displaced, right? But G point, your center of gravity, it is independent of whether it is submerged or partially submerged or whatever. So G will remain here only. So if you give push also, your G will not change. So we draw two lines here, and the lines passing through G and B dash, wherever they interact, that is your meta center point. So like that you can understand the metacentric height. So this GM, this GM, sorry, GM is what we call metacentric height. And based on that, again, they do the similar analysis where they apply some couple and they say whether body comes back to the natural, its original position or not. So depending on that, there are also three cases. Forgive me, I am not going into details of these derivations and all, but that is because of the time constraints, because this is like very small discussion class for that purpose. So let's say you have center axis for any body. Better to draw dotted because we are following that convention. So for any body, let's say you have three cases. So if your M meta center, G and B are in this order, so your GM is greater, or maybe how should I say, M above G, then this is stable equilibrium. And in some cases, what may happen, your G and M will coincide, so that will be your neutral equilibrium. And in some cases, your M will be below G, so this is M below G, so this is your unstable equilibrium condition. So yeah, this is the case for these things, floating bodies and all. You should know, we'll solve one problem based on this because otherwise many things are not clear here. So this meta center, it can lie inside a body or outside body, but the center of gravity and center of buoyancy, they always lie inside the body. So that is also one interview question. Maybe you can remember it like that. And okay, we'll take one question so that maybe this becomes clear. Let's say, see, I can take one question. Yeah. So let's take one question in which we are studying fully submerged case. So there are different ways to ask a question. Okay, I am taking a template, and maybe that will help us to tackle if any other similar type of question is asked. So this is very this thing, very common type of question. So let's say there is a body which weighs let's say 30 newtons in fluid with density 800 kg per meter cube, and this is completely submerged body. Okay, it's not floating or something like that. And same body when submerged in, let's say this is rho 1, in fluid with density. So let's say we are submerging it in some another fluid, denser fluid. It weighs 15 Newton. So what is the volume of the body? So this is also a very typical question. I can add one more question also here, like, and what is the weight of the body in, let's say, air. So air has a density 1, right? So maybe we can compare that way. So this is very typical question that is asked. Maybe you have seen it somewhere or not, but these figures may change. Maybe they'll give some different fluid densities and different weights, but it is essentially application of Archimedes principle. So let's say this is your first liquid, and this is that body, and it is fully submerged. So this is your liquid level, and similarly you'll have some another fluid, same body, submerged completely with second density. So as we know, when it is let's say I use some other paper, it will have its own weight that is always acting downwards, whereas it will experience some buoyancy force, let's say FB1 here in the fluid 1 and FB2 in the second fluid, which will be vertically upwards. So whatever weight that is shown in fluid 1 will be the, so that is called as apparent weight. Okay, so this 30 Newton and 15 Newtons, they are not the real weight of the body. They are appearing as this much weight when they are fully submerged. Real weight is different. So that is what is asked in the second part of the question. So apparent weight in rho 1 fluid is 30 Newtons. That will be the actual weight minus the buoyancy force. And what will be the buoyancy force? That will be equal to the this volume of the body into its specific gravity. Anyway, that you leave it. But the buoyancy force is nothing but the weight of the fluid volume displaced. And here, since the body is completely submerged, whatever is the volume of the body, same volume of the fluid is replaced when it is fully submerged. So what is the weight of that volume? That will be equal to let's say weight is again mg, right? But this is fluid 1, this is fluid 1, that is the key point here. density into volume, and again G will be the same. So similarly, here also the apparent weight is 15, so that will be actual weight minus the buoyancy force experienced in that liquid. So that will be equal to FW minus rho of that liquid, because that much fluid is displaced into the volume into G. So now you have equation 1, equation 2. So you have two equations, two unknowns. What are the unknowns? W and volume, V. And you have two equations. So you can easily solve. The simplest way to go about it is subtract second from 1. So on the LHS you'll get 13 minus 15, and WW will get cancelled, and here you'll get volume, and this is common to them, so it will become rho 2 minus rho 1. I am assuming that you are understanding this algebra. If not, you can do it yourself also. It's not that difficult. So here now we can solve this. This will be 15. Volume is unknown. Let's say we'll take G as 10 meter per second square. Rho 2 was given in the question, which was 1200, and rho 1 was 800. So this will be 400. So your volume will be, let's say 3 to, so it will be 3 by 800 meter cube. I'm not giving you the exact number, but you can do the calculation. That is not that difficult. And then you put this value in any of the equation, then you get W. So put this volume in, let's say, equation 1. Then what you get? 30 is equal to W minus rho 1 is 800 into 10 G into volume, it is 3 by 800, right? So this 800 goes. Okay. 1 second. Did I do something here wrong? Because W 30 minus 30 is 0. So apparent weight is 0. 1 second. I think I am doing something wrong here. If you put it in 2, it becomes 15 minus W. I think I am doing wrong. We can't calculate it this way because it is giving some absurd value. So let me see what it says. So we got the volume. Okay, volume is okay. That much is there. One second. How do you see the chat? Anybody wants to help me out here? It should not happen this way. 800. 15, 10, 400, 15 by 4000. One second, let me just check where that question was taken from. because see, the first part is correct. This volume is correct, which was asked here. See, W value should be greater than 15 and 30 for obvious reasons. So, from equation 1, W will be 30 plus FB1. Oh, I was solving it correctly only. Instead of adding, I was looking at the subtraction. Anyway, so 800 into G is 10 and your volume is 3 by 800. So it is 30 plus 30, 60. I don't know why I was subtracting it. So anyway, that was a very naive mistake. So this is the pretty frequently asked question from this fully submerged case. And here maybe the dimensions of this body are not given, therefore we don't know about the stable equilibrium or neutral equilibrium or unstable equilibrium case. For that, let's go to the other example in which you consider something like floating equilibrium. So we'll take that question. So let's say
this W is apparent, sir. It is the apparent weight.
No. Apparent weight was 30 and 15 in that respective fluids, but when we take air, so there actually it should not be air also. It is what is the weight of the body, because W is the actual weight of the body when there is no buoyancy. Typically, ideally speaking, it should be in vacuum, but since the density of air is very low, we can consider it as a weight in our normal air also. So that is there. Now we'll take one question on the this thing. This is actually a subjective question because you know there is something called as engineering services exam. So there, I think it was asked. I don't remember the year, but this was actually a very good question. So you'll understand this floating equilibrium conditions. So they mentioned that there is one cylindrical object, solid cylinder. It is like this, and it is floating, and this is the water or maybe whatever is the fluid, that level. This is the free surface. It is not completely submerged. Okay, this is the other case. This is floating thing, and the diameter is given as d. The total length of the body is L, and it is submerged up to depth which is H. And it is mentioned that it is water. The fluid is water here. So this is the given information, and it is like this. It is floating. So now the question is, and this water density is 1000 kg per meter cube, and this body density, let's say we'll note it by rho only. It is 600 kg per meter cube. So this is given to you. Now the question is, you need to uh, I'll write it down. find the value of L by D ratio. L is the total length and D is the dia of the cylinder, so that body remains in neutral equilibrium. So this is the question. I can ask another question also. I can just say, instead of neutral equilibrium, what if I want stable equilibrium, unstable equilibrium? I can do all that, but this is what is asked, and other given data I have given you. So let's start this question. So since this is a floating case, uh, now we need to take this approach. We need to find this meta center, center of buoyancy, center of gravity of the body itself, and then in neutral equilibrium, your G and M point, they will be same. So the distance between G and M will be 0. So we will use that property to solve this question. So before going there, uh, let's let's do some simple things which we know. Let's draw the center axis. This is given in the question that this body is a homogeneous body, so don't worry about the other inhomogeneities. So now, as we know, this is a homogeneous body, so the center of gravity will be at L by 2. Maybe I'll draw the figure again. So this is the central axis, and let's say the body started from here, and let's say this is the end point of the body. I don't know why I'm using the same color. Anyway, so like this. Okay. So this was your length L given in the question. So as we know, this is a homogeneous body. So your G point, which is the center of gravity, will be at distance L by 2 from both the ends. So let's take it as 0.5 L. And this body, it is submerged, not fully. It is submerged, let's say, up to certain depth, which is given in the question as H. So your center of buoyancy, maybe I'll use some other color. So see, can I copy this one? 1 second. So this was your body, right? Now we know the G location. Now we are interested in finding the other 2 points, M and B. So this was your layer, free surface, and only this much volume is submerged, which is highlighted in this different color. This much volume is submerged in water, right? So your center of buoyancy will be the this centroid of this area. So this will be your B point. And what will be the B point? So this was the H, total depth, submerged level. So this will be the H by 2 level. I am just finding some easy things first, because that is easy, and then we can shift to the difficult part. So now this much is what we know. Okay, so we'll go ahead. Now we'll use first, in any question regarding the buoyancy and all, first you use the Archimedes principle. So Archimedes principle, what it says, whether body is submerged fully or partially, the buoyancy force will balance the weight of the body, and the buoyancy force will be equal to the weight of the fluid displaced. So here from Archimedes principle, buoyancy force will balance the weight of the body. So what is, let's say, weight of the body? So now what is the weight of the body? This density of the body rho into volume of the body into g. And again, this buoyancy force is equal to the uh, you know weight of the fluid displaced. Here, what is the volume of the body? Now this is a cylinder, so volume will be pi d square into L. That is the total volume of the cylinder. And here, fluid displaced. So what is the weight? So it will be density of water into fluid displaced into g. So remember, there is the volume of the body and volume of the fluid displaced will never match. The weights will be balanced, but volume will be different. Otherwise, the body will be completely submerged. If it is floating, that means the volumes will be different. Therefore, I am using this volume of fluid displaced, so VFD symbol for that purpose. And from figure, let's say this blue color figure, what is the volume of fluid displaced by the uh, body? It is equals to the pi d square, because that is the same area, but it is displacing only h level volume, right? Up to h level. So these two things should balance. So therefore, rho g pi d square L is equal to rho of water into g into pi d square h. So g goes cancels out, pi d square cancels out. So what is remaining is rho L is equal to rho W into small h. Now rho is given in the question, which is 600 kg per meter cube into L, and water density is 1000 into h. So from here, what you get? H is 0.6 times L. So now we have some more information, right? So now H is 0.6 times of L. So if you go to this figure, this H is equal to 0.6 times of L. So half of the H will be 0.3 times of L. So this information also we have now. So okay. So now what we'll do, we'll make a composite sketch. Actually, I did not mention this when I introduced the concept of metacenter, and this BM is called as metacentric height. So there is a formula to calculate metacentric height. Again, there is a derivation for that also, but that is out of syllabus for our course. So we need to understand, like we need to remember the formula, but the rationale behind that, maybe in some higher studies you will get to know it. But due to time constraints, I could not mention it there, but I'll mention it here, so you can uh, remember that. Anyway, so again, going back to the this image, you have center of buoyancy somewhere, center of gravity somewhere in the body, but this meta center, it can be anywhere. Okay, no need to be inside the body or outside the body. And you know, this center of gravity is, see, from this figure, if you see, okay, maybe I redraw the figure here. So this is our body, right? And this was our free surface level, and this was our, sorry, this is our center axis, and we know this is 0.6 L. So B point, which is roughly at the center of this B, it is at 0.3 L, and we know that G is at half of L by 2, so it is again 0.5 L from bottom and 0.5 L from the top. So therefore, distance between B and G from this figure, if you can properly visualize, it will be 0.5 minus 0.3 into L. So it is 0.2 L. So we know BG, this distance 0.2 L, but we don't know about M. So for the metacentric height, which is BM, it is typically calculated by using the formula, which is inertia of moment about the the center axis divided by the volume of the fluid displaced. So for cylinder, if you consider the center axis, the dotted axis that we have been using, this is the standard value, pi by 64 into d power 4, and again volume of the fluid displaced, which we uh, studied earlier also, it is pi d square into small h. I know some of you may have doubts that how come this formula came and all. I totally understand, but the derivation is out of the scope of this syllabus, and therefore just get the notion of the formula. So you can see the numerator is the moment of inertia, so that is fourth power d power 4, and in the denominator you have volume, so that is meter cube, or length cube. So when you divide this, you get some length scale. So if you do the dimensional analysis for this ratio also, you will get some length as the unit for BM, and that is what we want. So if you do this, you will get some, in the pi will get cancelled, d power 4, so only d square remains at the top, 64 into h. So oh, one second. Actually, this is pi d square by 4. Anyway, it is getting cancelled. It should be pi d square by 4. It can be pi r square, but when you are putting it in terms of diameter, it should be pi d square by 4. And here also it should be pi d square by 4. So there is a 16 will be remaining, and we know h is equal to 0.6. So if you put that, so that becomes d square 16 into 0.6 is 6L by 10. Then if you just simplify, this becomes 10d square upon 96L. Okay, and now you know this height also, BM, which is 10d square by 96L. So now see, in the question only it is asked that what is the condition for neutral equilibrium, right? But I can ask any type of question on this. I can say what is the condition when you have stable equilibrium. So let's just solve the question. So for neutral equilibrium, G and M point coincide. So distance between G and M will be 0. So that means 10d square by 96L will be equal to the 0.2L, or maybe 2L by 10. So from here, what is asked in the question, d by L, right? Or L by d, okay, L by d. So you can rearrange the term, so you get L square by d square equal to 100 divided by 96. So this is the 25 divided by 24. So therefore, L by d is square root of 25 divided by 24. This is 5 divided by, what is the square root of 24? How can we write? 2 root 6. Yeah, I think that is correct. Or maybe 1 second. Final answer is not matching. Why so?
Sorry, 4.90.
Hmm?
The 4.90, sir.
Yeah, that is okay. I'm just, uh, 48. Mm, did I do some calculation mistake? Yeah. I missed this too. See, this is 12 by 10, right? So 96 into 2 will be there, na? Array. So this becomes 96 into 2 is 180, 192. 192. And if you divide it by 4, it will be 48 here. Yeah. So square root of 48 is 4 root 3. So like this is your final answer. This is actually a subjective question, so maybe like 20 marks question this was in the exam. I think ESE or maybe civil services somewhere. But I can make another question also. Like let's say I can ask second question, right? What is the condition, or what is the value of L by D for which body is pushed into unstable condition. So this is just a question of asking something fancy, but if you understood till now, in the first part we took Gm equal to 0 because in neutral equilibrium M and G will coincide. But if you want unstable equilibrium, Gm should be less than 0. And if you do the same calculations, that will give you L by D less than 5 by 4 root 3. So if this condition is there, if your body is having L by D ratio less than this, your body will be always in unstable equilibrium, assuming it is having density of 600 kg per meter cube and it is floating on water, like that. So I think we'll stop with the hydrostatic part now because I've taken a lot of time on that. Fluid dynamics, also we have a lot of things to consider, but we'll try to cover whatever today is possible. But we also have next discussion for fluid dynamics. So let me just once see what topics were covered in this course.
Is possible to solve this in full, this question?
Pardon, sir? Pradeep, pardon?
Can you solve this question in full, sir? This question.
It is solved only, no? See.
Okay.
Yeah, because earlier I asked you neutral equilibrium condition. Now I'm asking you unstable equilibrium condition. So in unstable equilibrium, your meta center will be below your G point. So your GM should be negative in our sign convention. And that will happen when your L by D, or basically L by D is, I think, aspect ratio. So if that is lower than this 5 by 4 root 3, then it will happen. Anyway, so just a minute, I just check what was covered in this week. So third week, right? Okay, control volume, Reynolds transport theorem. Okay,
That is what we covered the last class, third week, it is covered.
Yeah, so Reynolds transport theorem is covered. I think it is covered for mass and momentum.
Momentum, sir.
Yeah, so just a second. Conservation of mass is there. And then conservation of momentum. Okay, force balance. Okay. So have you gone through Reynolds transport theorem? Anyone? Have you understood it? Why do we define, like, why do we need Reynolds transport theorem first of all? Anybody? Guess? No one? So basically, I mean, this looks like a very simple question or very trivial question, but it is not. This Reynolds transport theorem is actually a very important this thing tool. If you are studying, let's say, uh, fluid mechanics, but there are two approaches, right? Okay, I'll just finish this part here. So there is something called as let's say, types of systems. So in thermodynamics, you might have studied system, surrounding. So whatever is the matter that is under your observation, that is called as your system. And whatever is the remaining part of the universe, that is called as surrounding. And then there are two types of systems. There is something called as control mass system, and then there is called as control volume system. So uh, see, as the name suggests, uh, control mass system will have you know the identity of mass that is inside the uh, control or the system. Maybe, for example, if you consider something like mm, what should I say? Hmm. Let's say if you consider simple example, you have a tank, you have liquid inside it, and after filling the tank is the gate is closed, so you cannot remove this water outside. So there is no uh, mass interaction from the system to the surrounding. So that is your control mass system. Uh, uh, Actually, the correct definition is not the amount of mass should be same. The correct definition is identity of the system mass must be same. So what do I mean by identity is if you have, let's say, 1 kg of water in the tank, uh, it should remain 1 kg, but the number of molecules or the type of molecules are inside which are inside this tank, that also should remain same. So maybe I can give you the counter argument. Let's say I have again one water tank, same. Let's say if this is 10 kg or whatever number you want to put, it is also having mass of 10 kg. And what is happening is I am putting some additional m dot inside from one inlet, and I'm taking out that same m dot from the other side. But at all times, the mass of your control mass of your system remains 10 kg. But the water molecules that are inside the system, that are changed continuously. So this is not your control mass system. For control mass system, the mass should not, I mean, there should not be any mass interaction with the surrounding, as well as there's the identity of the mass should be also same. So I hope you got my point. And as the name suggests, this control volume is the approach where uh, whatever maybe your, let's say same tank, if you consider, Now you don't you don't close the walls. You keep the walls open, and
Sir, can you please repeat a little bit? Sorry, sir. Can you please repeat the system mass versus that identity, sir? Identity one, a bit confusion is there, sir. Identity.
yeah, so see, that's why I've given this example at the bottom. So you have two water tanks. They all have, both of them have mass of 10 kg total mass. But in one, in the tank that is shown at the top, there is no inlet outlet. So whatever mass of water is there, the same mass of water will remain. You can heat it, you can cool it, you can transport it somewhere, but the molecules that are inside the tank, they will be same. So their identity is same. But if you consider the bottom case where I am putting m dot mass per second in the 10 kg mass, and I am taking out m dot mass in that same time. So basically, there is the mass of the system always remains at 10 kg, but the water that is inside the system is not the same uh, at any instant of time. I am putting some salt water sometimes. I am putting fresh water sometimes.
Got
I
it, sir.
am
Got it, sir.
so like that. So in control mass system, mass of the system should remain constant, as well as the identity of that mass molecules or particles should also be constant. So that is what control mass system is. And in control volume system, you don't care about the mass. What you do, you fix certain volume in the whatever volume of your choice that you want to observe, and you only observe that much volume. There can be addition of mass, there can be release of mass. So mass of the system is not constant here. There is a mass interaction with surrounding as well as energy interactions, but this volume, control volume, actually control volume is bounded by control surfaces. Control surface. So you only care about this control surface. Whatever is inside, whatever mass or whatever it is, you don't care. Only that much volume you care, and whatever is happening across that volume, only that much you care. And one key point is this control surface or control volumes can be fixed, can be moving, and can be deforming also. So sometimes when I draw a figure like this, uh, somebody may get the idea that it is always the fixed volume in the space. It is not like that. That volume can be deforming. It can be increasing or decreasing. For example, if you consider the process of filling a balloon, so initially balloon volume will be negligible, but as you put the volume inside, it starts expanding, right? The balloon stretches and the volume increases. So if my control volume was the volume occupied by the balloon surface in the space, so that keeps on changing during the balloon filling process. So my control volume system can have control volume or control surfaces that are fixed in space, or they are moving, or they are deforming also. So that is there that you should understand. So this is what control volume means. And so coming back to our basic first point, why do we need RTT or the Reynolds transport theorem? So Reynolds transport theorem, or RTT it is referred to as in short form, connects the control mass approach and control volume approach. So it is a tool that gives you the flexibility to analyze one system, or if, like, analyzing one system as control mass system be sometimes easy, or in case of fluid mechanics, the control volume approach is better because you cannot keep on analyzing the fluid particles, right? It is very difficult. So what you do, you only analyze certain volume, whatever is coming in, whatever is going out. You don't care about what actually, which kind of fluid is going in or whatever it is. Their identity may change with respect to time. And RTT is a tool which bridges these two approaches. It gives you a flexibility whenever you want to shift from control mass to control volume. And in fluid mechanics, actually, control volume approach is very uh, easier as compared to the control mass approach. And therefore, we use RTT to change control mass system equations to control volume system equations. So those derivations were, I think, done in the class. So I'll just write the final this.
So it is highly mathematical, sir. A lot of derivations were there.
Yeah. I'll try to simplify, because when you first study it, it looks like a very complicated mathematics formula, but it's not. I'll explain. So there are actually three terms there: d by dt, something volume integral. So CV is control volume, and there will be some beta density and this volume integral, so dV. And then there is another term which is your surface integral. So CS is, so this is CV is control volume and CS is control surface. And it is again given by rho into beta, and you have something called velocity into unit normal into dA, since this is a surface integral. So yeah, it looks very at the first glance it looks very very bad, but yeah, and beta is actually if you divide capital B by mass. So yeah, there is one more concept here. This beta is called as extensive property and extensive versus, once again, one property is extensive property and one is intensive. So this beta is called as intensive property and B is called as extensive property. So before we go into the RTT, I would like to explain what is this intensive property and extensive property is, because this intensive and extensive property question is asked in GATE, and it is, I think, in thermodynamics also you see this. It's not particularly, you know, this thing only related to fluid mechanics. You get across this term in thermodynamics also. Just 1 second before I go into that. I just want to see what is the next week's course, so that if we start this one now, okay, because next week I think we have Bernoulli's equation and other things. So okay, so what is intensive property and what is extensive property? So the definition says extensive property depends on the mass of the system, and intensive property, it is independent of mass of the system. So okay, definition is fine, but can anyone tell me one example of extensive property? Anyone? Okay, so the simplest example is weight, and I think volume also, because as the mass increases, volume also changes. So yeah, volume also you can consider as extensive property. And intensive property, anything, density, thermal conductivity, etc., etc., or anything like, one second. So what Reynolds transport theorem does is, this first term on the right hand side, which is dy dt of capital B system, that is called as a system integral, or rate of change of system, something like that. One second, I'll just confirm. Actually, it is easy to not to look at the mathematical equation and just understand what is happening. But since uh, this is the technical discussion.
One basic question, sir.
Yeah.
Actually, what in intensive and extensive properties are actually important in fluid dynamics? What they should
Okay.
be?
So let me ask you a question. Let's say you have 10 kilo of anything, any mass, 10 kg, and it is at, let's say, temperature 100 degrees Celsius. And what I do, I divide that mass into 50-50%. Let's say 10 kg, I divide it into 5 kg. So will the temperature of that mass change? I am not doing any heating or cooling. Okay, I have just 10 kg of mass, which is an ambient temperature. I just cut it into half, or maybe separated into half. Will the temperature of 5 kg part will change?
Should not change, sir.
Yeah, it won't change, right? So temperature is also one property which is independent of mass of your system.
I got it,
Uh,
sir. Yeah.
yeah, and when you do, let's say you had 10 kg of let's say rice. When you divided it into two part of 5 kg 5 kg, their volume will reduce, right, depending on the mass. So
Yes.
therefore volume is the property which is dependent on the mass of the system, and therefore we consider it as an extensive property.
Yeah.
Understood?
That's okay. Yeah, that I understand, sir. But yeah. But the its importance of in fluid mechanics, even if we don't understand, I think it is we can still solve the problems.
See, in fluid mechanics, what happens, I'll tell you, in the context of this Reynolds transport theorem, we consider four cases. We consider B as the mass, that gives you continuity equation. So this RTT equation that I've shown on the top, if you put capital B as your mass of the system, uh, then, okay, I'll make a table actually. So let's say I I take capital B as mass of the system, then your beta becomes, which is B by M, it becomes 1, right? Because mass by mass is 1. And this gives you, if you put this beta and B value in the RTT equation, you get continuity or mass conservation equation. So that is first. Second, if you put capital B as your linear momentum of your system, then beta becomes your velocity of the system, and this gives you linear momentum conservation equation. Third case, you put beta as your angular momentum. So angular momentum, if you remember, it is linear momentum into some moment. So let's say m One second. So m and some cross product of velocity and your moment, some distance r. So if you put that in the RTT, your beta will become r cross v, right? This angular velocity kind of thing. This is your angular momentum conservation equation. And fourth is, if you put your beta as let's say total energy, internal energy of the system, so your capital beta will become E by m. We typically write it as a specific energy of the system, and that is your conservation of, I mean, if you put this beta and b in RTT equation, you get conservation of energy. So I think this angular momentum conservation is not in the scope of this course. Maybe advanced level fluid mechanics, if you take, you will face that. But we will study this continuity equation, linear momentum conservation equation, and energy equation also later. So this is where, I mean, as far as I remember, only in these 3-4 equations you need to remember what is extensive intensive properties. But main application of extensive intensive property definition is in thermodynamics. There it is mainly applied. And one more thing, what happens? Let's say you are doing some experiment and you are getting some data, and it is always better to report intensive property, because, for example, somebody sees your results and they are impressed and they want to do something improvement in your work. So it is not necessary that both the experimental setups will be same, right? For example, uh, how should I say, uh, let's say I have 10 kg of water, and I'm going to heat the water by 5 degrees Celsius. So how much energy I'm putting, which is mcp delta t, right? So and the same experiment, if somebody is doing it with, let's say, 100 kg of water, so their heat requirement will be exactly 10 times that of mine. So it is very difficult to do comparison when you are reporting extensive properties. But if you are reporting intensive properties such as temperature, pressure, then anybody can compare those with their work. So typically in the academics, if you are reporting some results, then you tend to show extensive property. For example, I think I discussed Reynolds number in some of the previous class. So Reynolds number is also a non-dimensional number. Okay, so everybody can use that number to compare different things. So eh, like it is actually convenient to use intensive properties. Therefore, in thermodynamics, all the steam tables that you use, they all have enthalpy in kilojoule per kg, right? Internal energy is in kilojoule per kg. The specific volume is also is meter cube per kg. So they all of them are intensive properties, and since they are intensive properties, everybody can use it, and whatever mass of the system they have, they can just multiply with that mass, and they will get the extensive property. So that is the significance of extensive and intensive.
Yeah, clear, sir. Yeah,
Clear,
that's
no?
great. Yes, yes,
Yeah,
fantastic.
actually, this question was asked to one of my friends. He said thermodynamics is his favorite subject. I think it was BARC interview. So when he said that, they said, "Do you know steam table?" He said, "Yes." Then they said, "What all properties are listed in the steam table?" Then he told that enthalpy, internal energy, volume, specific volume, etc. So then they asked him, "Why do we report them on per kg basis?" So I think he was able to answer, but the point I'm trying to make here is this is not that simple concept. I mean, maybe you can appreciate it later, but yeah, basically it is easy for understanding or easy for generalization. That is why intensive properties are used. Anyway, coming back to this our discussion. So as I said, yeah. So, and if I am being conventionally correct, so this is the relative velocity. So as I said, right, your control volume can be fixed, it can be moving, and it can be deforming also. So in the last term, the third term, you take the relative velocity between your control volume and your inlet outlet fluxes. So anyway, I'll explain what this is. 1 second, if I can just copy this. Yeah, I'm not able to copy it. So, so this d by dt term, let's say the system. So this is your, we call it as total derivative. I think somebody calls it material derivative also, but total derivative or like that. So let's say if you have a control mass, let's say you have 10 kg of water in a container and there is no inlet outlet for that water. So as long as the water is not going out or coming in, this dm by dt, or let's say if I take B as mass of my system, then dm by dt should be 0, right? As long as uh, there is no mass exchange with surroundings. And so like that only. So whatever is your B, in one case you can take it as mass, maybe in another case you can consider it as linear momentum. So can anybody tell me what is the quantity that comes out when we take, let's say if we put B equal to linear momentum, what is dV by dt? It is d by dmv by dt. So can anybody tell me what is dmv by dt? Uh, Anybody knows Newton's second law? Anyone? Okay, so let's say if your mass is constant, then this becomes dv by dt. So this is nothing but mass into acceleration, right? So this is nothing but force. So if I am considering linear momentum conservation equation, this d by dt term, d by dt of capital B, it essentially reduces down to the net forces acting on your control system or control volume, whatever you want to call. If you are considering LHS, it will be system, but if you are considering RHS, it will be volume. So like that. So this is your total derivative of control mass system. But as I said earlier, in fluid mechanics, you cannot keep track of all the fluid particles at all times. So therefore, it is better to define a control volume in a space and you keep track of certain particles flowing through that control volume. So in that case, the second term in that RTT equation, which is, okay, so this was the first term. This is d by dt. There is a volume integral inside, Cv of rho beta volume integral. So d slash v. This is actually a term which signifies accumulation or destruction or deaccumulation. What is the opposite word of accumulation? One second.
So deaccumulation is okay, sir.
Yeah. I'll just check once.
That's what happened in deaccumulation.
Yeah, decumulation. Decumulation is the opposite word. Anyway, so the point is the second volume integral, what it says, whatever control volume you have, whether that quantity is getting accumulated or it is getting lost from the control volume of the beta quantity from control volume and with respect to time. So it is with respect to time. So basically, let's say at t equal to 0, you had 10 kg of water in your heat exchanger container. And when you switched on the heat exchanger, let's say after 15 minutes, only 5 kg is there. So that is getting decumulation. But after 5 minutes, if it is 15 kg, that means the water is getting accumulated slowly with respect to time. And the third term, which is again a time derivative of a surface integral, I have wrote it in very concise form here so that it becomes easy to write the equation, but it can be written as two parts, because this is a surface integral. So like the general sign convention says, whatever is going out of the control surface, you take it as positive, and whatever is coming inside the control surface, you take it as negative. I mean, there is a logic behind it, but okay, I'll explain that also. For example, let's say I have some control surface like this, and what is this small n dot n cap? Let's say at any point, I am defining one unit normal out vector n cap. So when I take dot product of relative velocity or velocity of okay, before that I'll explain what this is actually. This term signifies exchange of beta quantity with surroundings with respect to time. So basically, if your control volume does not have any inlet outlet, so essentially this third term will go to 0, and your control system and control volume, both equations will be giving same answer. But in case of fluid systems, which we typically study, such as a heat exchanger or maybe let's say some pipe flow, flat plate flow, there you have some inlet, some outlet, right? So this is why this term is important. And since it is a surface integral, I am just drawing on some arbitrary control surface, and outward normal is positive. This is a basic convention in geometry. And let's say I have some relative velocity direction this way, and this is their theta, the angle between them. So very small surface we are considering. So basically this is a dot product between these two vectors. So if theta is 0, this dot product is positive, right? Because cos 0 is 1 and it is 0. Therefore, outward fluxes are considered as positive. Flux is basically this exchange of quantity with surroundings. So flux is what is like coming out or going in. If any quantity is going in or coming out, that is there is some flux to it, right? Because there will be some finite area through which that quantity will be going in or coming out. So that is what is called as flux. For example, when you call solar flux, it is defined as amount of energy received per unit area, like that. So, and if theta is 180 degree, this dot product between relative velocity and output normal will be negative, and therefore inward fluxes are negative. So basically, in that case, you will have n cap like this, and your VR relative velocity will be like this. So this is when theta is 180 degree, and this is what inlet, right? So something is going in the control volume. In that case, it will be considered as negative, and something is coming out of the control volume, that will be considered as positive. So if you like take some time, because this is maybe for some people this is new concept. I think we'll stop here today because we are already at 8 o'clock. And tomorrow or maybe next week's class, we'll start with the continuity equation, some examples on it, maybe some linear momentum conservation equations. And I think next week's content of mostly it is Bernoulli equation. But I think it will be better if we cover them together, because I think Bernoulli equation is nothing but the RTT applied to a like you basically do conservation of energy. That is what Bernoulli equation is. Basically, it is mechanical energy conservation. You don't consider other kinds of energies. That is a typical case when you consider simple pipe flow. For example, if I say I have a water tank on top of my home and water is coming to my tap. So if I want to analyze this type of problem, it is very rare that the temperature of water will change from coming from top to bottom. So there, the thermal energy interaction is not that significant, but pressure drop is important. Because if at the tap, if I'm not getting enough pressure, that is a problem, right? So like that, there is like energy is a very uh, energy has different kinds of these things, different types of energies. So from total energy, if you exclude thermal energy part, what remains is mostly called as mechanical energy, and conservation of mechanical energy is nothing but the Bernoulli equation. So I think it is better if we see, now we discussed RTT, so maybe you can take some time and digest this if you have not understood already from class lectures. But I have tried to explain it in as detail as I can. In the next class, we will take some examples, and then maybe you will understand it more. And I think that is the better way to go about it, because right now we are already at full time, and if we start now, again there will be a break. So I think it's a good option that we stop now, and maybe next week I'll start with the continuity of, I mean, this RTT applied for conservation of mass equation. Okay.
Thank you, sir. Thank you so much. Very informative, sir. Thank you.
Okay. Anyone has any questions, or shall we stop? I think Pradeep asked whatever he wanted to ask.
Yes, yeah. Last question a bit. Last number 3 point was a bit difficult, sir. Actually, but I think we'll class. I think we'll go through it,
Yeah,
sir.
maybe just look at these terms whenever you have free time, or maybe next class, maybe it will be better. But see, in a nutshell, what I'm trying to say is, if you consider RTT, this volume integral, it is a significant, or it is a signifier of accumulation or decumulation of any quantity in the control volume. And the second term, which is the control surface integral or surface integral, that basically signifies coming in and coming out. Coming in and going out, something like that. If you have that understanding, So in case of conservation of mass, you can say the second term is like inlet outlet ports, and the control volume integral signifies the mass of the system, whether it is increasing over time or decreasing. Like that, you can understand that way.
So, yeah.
Okay, then we'll stop,
Okay, sir.
and
Yeah. Thank you, sir.
hope to see you next time. Happy
Thank you.
Independence Day. I forgot
Happy
to
Independence, sir.
wish at the start. Okay.
Thank you, sir. Thank you so much.
Okay. Thank you. Good night. See you next time. Bye.